By taking the average, you're assuming something, and you're assuming it implicitly. You're assuming what we call the bathtub model. If an ice sheet melts, so here's an ice sheet, it melts back down, here's old sea level, here's new sea level, you're assuming that sea level will rise uniformly if an ice sheet melts. That isn't even close to being true. In fact, an ice sheet, let's look on the right here, has mass. It exerts a gravitational attraction on the water near it. So water is gravitationally attracted to the ice sheet. If the ice sheet melts, two things happen. You certainly dump water into the ocean. There's no doubt about that. But the second thing you do is that you relax this gravitational tide. You relax the pull on the water. And it turns out that near an ice sheet, that second effect wins. If I'm standing at the edge of the Greenland ice sheet and it catastrophically collapsed, sea level at my feet would drop 100 meters. Highly counterintuitive, but not in any sense controversial. This is just Newton sitting under the apple tree. There's nothing, so many things that I do are theoretical or involve a sequence of parameters that each require some justification. This is just Newton's law of gravitation, right? So let's look at what the implications of this are. This is a numerical simulation where what we've done is we've melted enough from the Greenland ice sheet to raise global sea level 1 meter on average. If we added it all up, divided it by the area of the ocean, we'd get 1 meter. This is what actually happens to sea level. The blue here is the zone around Greenland where sea level falls. And what I didn't tell you when I saw this plot is that hinge point, how close is that hinge point to the ice sheet? Where do you go from sea level fall to sea level rise? It isn't near the ice sheet, actually. It's 2,000 kilometers away, which is roughly this distance in blue. So, if Greenland melted catastrophically tomorrow, and you happen to have a friend, I was giving a talk recently, and I made the terrible mistake of calling Scotland the northern tip of England, which I'll never do again. But if you have a friend in Scotland, they may be justifiably concerned, but they shouldn't be, except in some broad humanitarian sense, because sea level would fall in Scotland if the Greenland ice sheet melted. It would also fall in Newfoundland, etc., but you pay the price somewhere, and as you move further and further and further away from the Greenland ice sheet, you get more and more sea level rise. This is a 30% increase in sea level relative to this 1 meter that you predicted. But there's like a delta function, a very steep dip near the ice sheet, so that in this simulation, where we melted enough to raise sea levels 1 meter on a globally average sense, sea level would fall in Greenland by about 20, 25 meters. That is a very significant sea level fall. And the important thing is that these effects aren't just, I sort of cheated in showing you this picture by just looking at gravity. There are also deformational effects. When the ice sheet melts, the crust comes up, and that's also included in these analyses. But clearly, this geometric pattern is going to be distinct for each ice reservoir that might be melting. And that's why these patterns have come to be known as sea level fingerprints. The idea now is to look at fingerprints for all sorts of melting scenarios. This is the Greenland one I talked about. Antarctic will have its own fingerprint, where you have this zone of sea level fall nearest to the Antarctic. And glacier melting systems like Alaska, Patagonia, etc., will have their own zones of sea level fall around them. So now the question is turned on its head. At first we were told that if sea level varied geographically from place to place, it could not be because of ice sheets melting. In fact, it has to be, in some sense. If ice sheets are melting, the sea level change has to be geographically variable. And that variability tells you something really important. Now we can go beyond just saying sea level is rising in a globally average sense of value of so-and-so. You can actually, by looking at that geographic variation, tell where that meltwater is coming from. You can add these fingerprints up in a sort of least squares approach, and you can actually determine, with a few very good measurements of sea level change, you're sitting there in the ocean, it all looks like water to you, but by looking at the geographic variation of that change, you can actually infer which of the reservoirs were contributing how much